Okay, guys, so today we're going, I said there's basically these six topics that are tested on the free response portion of the AP exam, and one of them is motion. So I want to review that with you today, and I want to go over the graphs of the derivative homework that you had last Thursday. I've also given you guys the 2003 AP exam, the multiple choice to work on. Did anyone, if you did not receive that, just come on up and get yourself a copy. I have a video explanation. This time it's me, but you have to scroll to get to the question you want for every single question in here. And we'll be going over that soon. So, it's just hard because, I don't have you for that many days in class. And I want to make sure we spend at least a day each on these free response topics. But you got to keep practicing the multiple choice. The homework on motion, I didn't go to the 2014. I think there was a table involved, and I haven't focused on tables yet. So it's 2011, 12, and 13. Okay, so for the do now today, you're given the path. The path of an object is indicated, at time 0, its position is -2 on the number line. In calculus, in this class, we only consider motion along a line. It goes back and forth on a horizontal line or up and down on a vertical line. It's not going off into space. So it starts out at -2 at time 0. At time 3, it's at 4. And then at time 7, it goes back to -4. And I just want you to fill in the total distance, total displacement, and see if you can make a little sign chart for the velocity, just with that little information. Okay, so what's the total distance traveled by this object? I want to give an answer for that. All right, Jillian? 14. Does anyone agree? You do? All right. Then I think it's true. Yeah. Because it's going from -2 to 4, that's 6. And then from 4 to -4, that's 8. And 6 and 8 is 14. Now, total displacement, Cameron, -2. To get displacement, you don't care about where it turns around. It's just final position minus starting position. And so when you say it's -2, so that gives the person who hears, oh, the displacement's -2, I don't care what the guy did. Basically, he wound up 2 units to the left of where he started. So his displacement is -2. Now, the last part, make a sign chart. And we always deal with time starting at 0. So when does the velocity change sign? At what time? At what time does the velocity change sign? I heard it. 3. Okay. So from time 0 to time 3, is the velocity positive or negative? Positive. He's moving to the right. And then from time 3 to time 7, velocity is negative. That's when he's moving to the top. Now, I guess I'll go over homework first. Okay, I'll go over homework first, and then we'll get into I want to just do a review of motion problems, because those are fun. Okay, so I gave you guys the solutions to the 2012, 13, and 14 graph of the derivative AP problem. And so what I'd like you to do is tell me, if you could find that in all these notes, the answers, check yours, and see what you'd like me to go over. 2012, 13, and 14. We had both types in here. We have the accumulation function type, and we have the kind where they just said, hey, here's the derivative and a point. Just Ryan. 2012 part C. Well, I don't want to sit here and do your homework for you. I want you to actually try it, and then wherever you get stuck, go through it. Okay, 2012 part C. Find the x-coordinate of each point at which the graph has a horizontal tangent line. Okay, so horizontal tangent line means the slope of the tangent must equal what? 0. So the first question is saying, where is the derivative 0? All right, and now we're looking at, and the graph of G has a horizontal tangent line, so when its derivative G prime, which at this point in the problem we've established is this graph here, is 0. So it's going to equal 0 here and here, right, at negative 1 and 1. Okay, so that's the first part. So it has a horizontal tangent at x equals negative 1 and x equals 1. And then they said, for each of these points, determine whether G has a relative min, relative max, or neither. And, to have a relative min, it must change from negative to positive, relative max, positive to negative. And so at negative 1, it's going positive to negative, that's definitely a max. But what about at positive 1? Neither. It's not changing sign. See, the slope of G is negative, and then it goes to 0. So just for a second, the slope is 0, and then it goes to being negative again. So it's not a min or a max at 1. But at negative 1, we have the relative max. Questions? Yes? Of this one? Okay, so you're okay with G prime? That's what you're looking at, and you had to figure it out in this one. But G double prime of negative 3 is the derivative of the first derivative. So it's the slope of this one at negative 3. So when we look over at this graph, at negative 3, thank goodness, G prime is linear. So the slope at any of these points will be the same. Now to get that slope, we just use any 2 points on the line, and we use the slope formula. So this one, you see how it goes up 2 over 2? So this, at any point, the slope of my first derivative is 1. So the second derivative is 1. Or any value of x they gave me over here. Negative 3 is in here, so it's 1. So the second derivative is the derivative or slope of the first derivative. Okay? Yes? 2013 Part D. Okay, this is the function g. Oh, good. The function g is defined as g of x is equal to f of x cubed. And they want us to find, and they also tell us that f of 3 is negative 5 halves. Find the slope of the line tangent. Oh, let's translate that. Find the slope, find the derivative to the graph of g. So find g prime, the derivative of g, at x equals 3. This is what we have to find. And they also gave us that f of 3 is negative 5 halves. Okay. Well, if we have g of x, before I get g prime of 3, I have to get g prime of x. I have to figure out the rule. Chain rule. Beautiful. So what's the derivative of the outermost function? 3. Yeah, f of x squared. Yeah, don't forget to reduce the power by 1. Then chain rule, we have to multiply by derivative of the inside. So we get the rule for g prime of x. So that means that if we want g prime of 3, that would equal 3 times f of 3 squared times f prime of 3. I'm just putting 3 in for all the x's. Now f of 3 is negative 5 halves. So we have 3 times negative 5 halves squared. Now what are we going to do for f prime of 3? Oh, yeah, we got a graph with f prime. So f prime of 3, if we read the graph, is 4. So we have 3 times 25 fourths times 4. The 4's would cancel, and we get 75. Let me see this coming through the chain rule in there. questions on any of them? Yes. Nice. We're going over here. Yeah, those 2014D, and this is one of those accumulations. So the function p is defined as p of x equals f of x squared minus x. Find the slope of the line tangent to the graph of p where x equals -1. What does this mean? Find the slope of the tangent to the graph of p at the point. Yeah, so we have to find p prime of -1. So first, we have to get p prime of x. This must be something they like to do now. They've done that in 2 recent years. So we'll use the chain rule. So p prime of x, right? What should I write first? F prime, we leave the inside alone, so x squared minus x times 2x minus 1. Okay, so that's p prime of x. Now everywhere we see an x, we'll put in a -1. So it'll be f prime of -1 squared minus -1. Maybe I better write it. -1 squared minus -1 times 2 times -1 minus 1. Okay. So first of all, what is -1 squared plus 1? -1 squared is 1 minus -1, so plus 1, 2. Okay. And then 2 times -1 minus 1, -3. Okay. Well, this is the type where you had to figure out that what you were looking at. Oh, this is f. Ooh. So I was gonna say, oh, this is the graph of f prime, but it's not. It's the graph of f. How am I gonna get f prime of 2? 2 is right here. This is f. How do you get f prime, or the graph of the derivative? I should say the value of the derivative at a point. Slope. That's why it has to be linear. You can't do it. It has to be either linear or 0. So let's find the slope of the entire line segment. And because it's the same everywhere. Actually, we could use this point here. This is 2, 0. So on this, change of y's over change of x's is going to be negative. Negative what? Goes down 4 over 2. So it's -2. So f prime of 2, as well as f prime of any other point in there, is -2 times -3 equals +6. You see it? See, I was thinking we were going to do the exact same thing as last time when you asked that one. And, oh, yeah, this is f. We needed f prime. Okay, anything else from these questions? Oh, well, the one we used in the area volume section, we did pi over 8d squared. It's just 1/2 pi r squared. Yeah, pi r squared is the whole circle. Yes. Same question, part C. Now they want us to find the derivative of h. At least they're saying they want h prime of 3. So first we got to get h prime of x. Okay, looks like we got a little loady high. Let's write out the rule first. So low is 5x d high, g prime of x, less high. What's d low? I should put the 5 in front. Oh well, I can't fit. All over the denominator squared. Okay, we want h prime of 3. So h prime of 3 is 5 times 3, or 15, times g prime of 3 minus g of 3 times 5 all over 15 squared. Now in this problem, this is how g was defined, and we right away we know to take the derivative of these. So g prime of x is equal to f of x. So we're looking at a graph of g prime. So to get g prime of 3, we just read the graph. The only problem is they didn't label the point for us. Thanks, College Board. So now we don't even know. You know, the slope we just figured out was -2. So if it's at 2, 0, and you go down 2 over 1, where are we? We're at 3, -2. So g prime of 3, we can read from the graph. That's the -2. 15 times -2 minus, oh boy. Well, you know, it'll be 5 times g of 3. To get g of 3, I have to look at this definition. Oh, we did in part A? Now, are you okay getting that? Yeah? To get the value of a definite integral from the graph, as long as this lower limit's less than it is, you do area above minus area below. So I look at this graph between -3 and +3. 1, 2, 3. So from -3, wow, so we have a lot of area above. We're going to take all this area, and then we're going to subtract this little guy. That's going to subtract the area below. So the area below, 1/2 1 times 2. 1. What is it going to? So it's just going to be 1. Yeah, 1. And now the area above triangle. So 1/2 the base, which is 5. I better write that out. 1/2 5 times the height. 1. I can't even see. I don't even know what I've done here. It's 4. I'm just going to believe you. So you always take half the even number first. It makes it easier. So 1/2 of 4 is 2 times 5 is 10, right? So 10 minus 1, because area above is 10, area below is 1. So all that is 9. Well, times 9. So let's see if we have a chance of getting this right. We have -30 minus 45. So it's -75 over -225. It's just 1/3. Positive 1/3. Whoops. Copied that wrong, so then it's -1/3, isn't it? And you don't have to reduce it, of course. You don't. No, these you can be pretty much guaranteed. Every single example here was no calculator, right? And these are never calculators, especially now that there are only 2 questions they allow you to use calculators on. They really, you can pretty much count this one not being a calculator question. Do you like these? They're not the worst, right? Yeah. Anything else on these? We talk motion? All right. First of all, say something positive about motion. If it wasn't for motion, we couldn't move, right? So I think we all agree that we need this. Well, I think, you know, when you first see motion, like when we started in the beginning of the year, it seemed overwhelming. I think when you go back to it at this point of the year, it's really not so bad. Let's see. Maybe it's even worse. Okay, so we did this do now. We're going to go through an overview of everything. Now, here's the thing. When you get a free response question with motion, ladies, usually they're going to give you velocity. Because velocity is like the middle guy. Now you got position, you got velocity, you have acceleration. Velocity is a good one. Sometimes they'll give you the equation for velocity. Sometimes they'll give you a graph, and sometimes they'll give you a table. Okay, you never know how you're going to get this. But the first thing you got to be able to do if you're given an equation of any of them, you have to know how to get from one of these equations to the other. So if you want to differentiate, what is v of t the derivative of? Position. What about acceleration? What's that the derivative of? Yeah, that's the derivative of velocity. And since it's the first derivative of velocity, and velocity is the derivative of position, it's also the second derivative of position. Now you can also get to another equation by integrating. V of t is the antiderivative of which one of these? Acceleration. Now every time you find an equation by integrating another one, you wind up with a plus c, right? That's the annoying part, going that way. Which you can always find, if they give you a point on the graph of the velocity, you can figure out c to the velocity. How would you get to position by integrating? What would you integrate? Velocity. Very good. And again, if you do that, you're going to wind up with a plus c, which you can solve for if they give you a point on the graph of the position. And you don't have to memorize all these separately. Remember, we had that SVAT, spot, right? When you want to go in this direction, you take the derivative. Derivative of position is velocity. Derivative of velocity is acceleration. And if you want to go in that direction, you take the antiderivative. And the reason we have the t here in spot is because it's with respect to time. It's per change in, per second, per minute, whatever. All right. Now, even if you didn't have a calculator, but let's say you had a calculator and you're given the equation of velocity. How do you get displacement on the interval from A to B? Say it again. Okay, S of B minus S of A, but now let's say you're only given the equation of velocity. You don't have the position function yet. Yes. You would integrate velocity from A to B because that's going to give me exactly what you said. You take the antiderivative of velocity, and that gives you position, and you plug in upper and lower and subtract. So you have to know that if you want displacement, you take the definite integral of velocity from A to B, and that'll give you the position at B minus the position at A. I didn't write it out because I don't know if that would make it more confusing. Because the antiderivative of velocity is position, and that's the definition of displacement. The velocity, the equation of the velocity. So something like this, if you had your calculator, you would just do math 9. You put in your velocity, comma, actually you have to do comma A, comma B, and that gets you the displacement. Now, let's say they didn't ask for displacement, they asked you for distance. And you have your calculator. And I'll give you something to think about. Maybe that'll help you a little bit. So let's say you have your velocity. Yep. Okay. Definitely that's a thing. If you don't have your calculator, you have to break it up. Every time the velocity was 0, and do these separately. Because if you just integrate from beginning to the end, let's say this is A, this is B, if I just drew that a little better, it would have been 0. That's not your distance. Because it's traveling this far to the right, whatever that area is, and then it's traveling this far to the left. Yeah? Yeah. Yeah. When you put absolute value around the velocity first, then integrate, think about what it does to the graph whenever it's negative. Then when you integrate, you get the total area, which is the total distance. So you don't get, how far right minus how far left. You get how far you move right plus how far you move left. That's the secret. So if you have your calculator, they ask you for total distance, just integrate the absolute value of V of t from A to B. If you don't have a calculator, then you have to find out when the velocity is 0 and do them separately. Integrate velocity from A to this value, okay? And that'll give you how far it goes to the right. And then you'll have to, when you integrate from C to B, the velocity, you're going to get a negative value. So you could just subtract that. And that would give you a total distance. Okay, now, this is again something that keeps coming up. Let's say you have your calculator, and they gave you the equation for the velocity, and they also told you the position at some time A. And they want you to get the position at some time B. Oh my gosh, you're saying something good here. All right, is that S of A plus what? From, you want to say A to B, then say it because it's right. Of what? Yeah, the derivative of position function is the velocity function. And you always integrate the derivative to get the total change. So if you want to know the position at B, take the position at time A and add the change in position from A to B by integrating its derivative. So like it's S instead of F, S position. And really instead of F prime, we have B. What's that? Oh, yeah, well mine are. Other people's look, yeah, mine do look very similar. That's the daddy and that's the baby. Yeah, I wish I made mine look a little better. Okay, now let's say you have a graph of the velocity. So last one we had the equation, we had our calculator, we were happy. Now they just give you a graph. And let's say, oh, I'm not very imaginative. Okay, so A, B, and this is a graph of the velocity. And they ask you for the total displacement. Now think about it. We already said how you get total displacement. How do you do that with a graph? Area above minus area below. So the total displacement is the integral of the velocity from A to B. So what we do to get a definite integral from a graph is we do area above minus area below between A and B. Nice. What we just did before? Well, before you would have you would just pop it into your calculator. You would do math 9. It is that. It's still the definite integral of velocity from A to B, but how you get it, if you didn't have a calculator and it was an equation, you take the antiderivative, plug in upper and lower, and subtract. But now I'm saying, now we don't have the equation of velocity. We have just the graph of it. So now we're going to evaluate a definite integral using areas. And then total distance, we already said, was the definite integral from A to B of the absolute value of velocity. What are we going to do for that? Area above plus the area below. So good. Plus the area below. Right? That'll give you how far to the right it traveled, plus how far to the left. That'll give you the total distance. Nice. Okay, an object changes direction when the velocity graph. How would you know when looking at a velocity graph when the object changes direction? Crosses the x-axis. I could say t-axis, but we're all thinking x-axis. All right, so it actually has to cross. It can't just touch and go back. It has to actually crosses. Nice. Okay, now remember the object is speeding up when velocity and acceleration have the same sign. This occurs when the velocity graph is above the x-axis and when the velocity is positive, when its graph is above the x-axis and increasing, because then the acceleration would be positive too. Acceleration is just the slope of velocity. So when the velocity graph is above the x-axis and increasing, or they could both be negative, below the x-axis and decreasing. can use a sign chart for this thing and the thing. Sure, you can also thing. Okay. Now, if you're given the graph of the velocity and you're asked for the average velocity, first of all, how do you get the average value of a function? Not the average rate of change. That's the average rate of change. So it would be 1 over b minus a of v of t. Yeah, now, but again, I only have a graph of the velocity. So for this part, the definite integral velocity from a to b, how do we get that? Above minus below. I like that. You just like cut it down. So I like it. So see, I don't know if I'm cool enough to write that. Above minus below. I don't know. Like, I feel like I'm the kind of like area. I gotta stick it. Now it does turn out that the average velocity, think about it, is the average rate of change of the position. Because if you integrated velocity, I don't want to like make your head go, but if you integrate velocity, you get position. So this would just be s of v minus s of a, change in position over change in time. It's just that if you're working off the graph of velocity, this is how you'd want to do it. It is the average rate of change of position. Okay, now, again, we're given the velocity graph, and they say find the average acceleration on the interval from a to b. Yes. Oh, yeah. It's just you use the slope formula, because acceleration is the rate of change of velocity. It's the derivative of velocity. So it's just v of b, change in velocity, v of b minus v of a over b minus a. Like in my little drawing there, the average acceleration, what does it look like it would be from a to b? Even though the slope's changing, like the velocity's changing, what do you think the average acceleration would be? V of b minus v of a. Looks like it's going to be 0, right? It's the slope of the secant. All right, what else we got here? Whoa. Instantaneous acceleration at time c, and it would have to be linear. But how would you get the acceleration at a particular time if you're looking at the velocity graph? Acceleration is the derivative or slope of velocity. So you just find the slope. You'd find the slope of the graph of v of t at t equals c. That's why it would have to be something linear. So if they gave you the graph of the velocity, they'd have to pick a time that was part of some line segment. So you could figure out the slope of that line segment. I gotta speed it up, don't I? Do I have much more? Oh, no, I barely have anything else. This is good. The last thing they could do is they could give you a table of values. And let's say they gave you a table of values or chart of values for the position. So they gave you for certain times the position. If they said approximate the velocity at time A, you just use two nearby points. So like if they said approximate the velocity at time 3, and they gave you 1, 2, 5, and 7. 7, 3, 1. I just made up these points. But if they gave you the positions at certain times, and they said approximate the velocity, ooh, I wrote v prime, I meant s prime. Approximate the velocity, which is equal to the derivative of the position. What formula would you use? Yeah, which ones would you use? You'd want to use these 2 points, right? Because 3 is right in there. So like 1 minus 3, change in position, over 5 minus 2. See where I'm getting that? because its velocity is change in position. So difference in positions, 1 minus 3 over 5 minus 2. So it'd be negative 2/3. That'd be an approximation. That's all you can do because you're approximating the slope of a tangent line just using the regular slope formula. And if they ask you for the average velocity over the entire interval, then you can do it. Again, it's just the slope formula. Average velocity is going to be the same as s of, oh, I wrote it here. So in our case, we could take s of 2 minus 1 over 7 minus 1. So average velocity, two ways of thinking of it. You can think about, yeah, it's 1 over b minus a times the definite integral velocity, but it's also equal to this. Okay, so guys, you're going to work on these three motion problems. You going to do it? Pay attention to which one's calculated and which one's not, because these could go either way. Try to do them the way they're intended to